Hello friends, I hope you all are well. So we have started with our topic that is satellite orbit and inclination. So continuing from where we have left, let's begin our topic with our first topic that is satellite location with respect to the earth. So in this topic we have to determine the satellite location with respect to the center of the earth. But at most times at most times we have to locate we have to locate satellite satellite location which is not the center of earth. So for this we have we should know some parameters or transformations by which we can determine the location of satellite. So let's take a reference frame, or you can say an equatorial plane, where we will using a coordinate system known as the geocentric equatorial coordinate coordinate system. Now, what is this geocentric equatorial coordinate system is? As you can see in this image, we have used a rectangular coordinate system, or you can say the geocentric equatorial coordinate system, whose origin O is the center of earth. The fundamental plane, the fundamental sorry not fundamental plane fundamental direction is the vernal equinox, and as per the right hand convention right hand convention right hand convention the y axis is at 90-degree eastward of the equatorial plane, whereas the z axis coincide the polar axis, where the earth rotates around its polar axis, which is the north pole. Okay, so as you can see here, this z axis is here, y axis is here, and z is axis here, and origin is O. I hope this much is clear to you. So the angle now the angle that which the orbital plane makes with the equatorial plane. Okay, so the angle at which the orbital plane makes with the equatorial plane is called inclination, whose interval is from 0 to 180 degree. If angle I is at 0 degree Celsius, then it is known as equatorial plane, and if angle I is at 90 degrees Celsius, then it is known as polar orbit. But if angle I is neither 0 degree nor 90 degree, then it is known as inclined orbit. As you can see in this image, this is the inclined orbit, whose angle with the equatorial plane, or the fundamental plane, is neither 0 or nor 90 degree. I hope you understand this much. So Furthermore, if this inclined or equatorial orbit of the satellite and the equatorial plane that revolves in the same direction, if both of them revolves in the same direction, then it is known as prograde orbits or direct orbit, which is less than less than 90 degree, and if it is greater than 90 degree, then it is known as retrograde, means it revolves opposite to the direction of the equatorial plane. Okay, so I hope you understand this much. Now the x-axis, which points towards a fixed direction. As you can see here, this x-axis is pointing towards a fixed direction, since the fundamental plane move does not move when the earth revolves around the sun, because earth revolves around its own axis on the polar axis. So this this x-axis, or you can say the fundamental direction, or the vernal equinox, is known as the first point of Aries. Now this first point of Aries is taken as a reference for the measurement of the angular distance in the eastward direction. Now we have a term for this angular displacement measurement, which is known as right ascension, or you can say RA, which is denoted by ohm. Okay, so the first point of Aries. Now what do you mean by a first point of Aries? It means where the day and night duration is of equal length, means where duration of day is equal to the duration of night, and what date it comes on March 21st. I hope you understand this much till now. So now when uh, so when the satellite penetrates this equatorial plane, there are times when the satellite revolves around its orbit, penetrates the Earth's equatorial plane. That points is known as nodes, and we have two nodes. That one is ascending nodes and another one is descending nodes. Now what is ascending node is? Ascending nodes are the ones when the satellite moves upward direction, that is from south to north. Second one is the descending nodes. This one is the opposite of the ascending nodes. This one is when the satellite moves downwards direction. That is north to south. Okay, so I hope till now you are clear there what are nodes. Okay, this one is where this satellite orbits the equatorial plane of the earth, of the planet, of any planet. Right? We are taking it with respect to the earth, so we are talking about with respect to the equatorial plane, or the reference plane. So in space, generally there is no up and down or right and left. Okay, So we are why we are saying that ascending nodes is move when the move satellite moves in the upward direction, or descending node when it go downwards direction. We are specifying it because we are considering uh taking taking the parameter of the Earth's gravitational force. Earth's gravity, we are taking it in consideration. Okay, so we have another point of interest, another parameter of interest, which is the argument, of perigee. Now, what is the argument of perigee? So it is the angle. It is the angle. It is the angle which is between ascending node ascending node to perigee. This argument of perigee is used to measure in the orbital plane orbital plane at the Earth's center in the direction of satellite motion. It usually defines the orientation orientation of an orbit in the satellite plane, and it is denoted by omega. As you can see here, this is the argument of perigee. Okay, so with this we can now summarize the parameters which can be used to define the satellite orbit in space, which is number one is I, which is inclination. Second one is A, which is the length of semi major axis. Number 3 is E, which is the intensity. Number 4 is ohm, which is the right ascension of ascending node. Number 5 is omega, which is the argument of perigee. But we have another parameter, the sixth parameter, which is V, which is the true an anomaly. Now, what is true anomalies? It is the angle from the perigee of the satellite position measured at the Earth center, or you can say it is the true angular position of the satellite in the orbit as a function of time. Now, what does these parameters do? So, as you can see here in this image, they are all the parameters of the to determine the satellite location. This V, omega, ohm, I, and A. Okay, so I and omega, it is used to tell the orbital plane position. Okay, second one is A and E, which is the semi-major axis, length of the semi-major axis, and intensity. These two parameters tells us the shape and size of the orbit. Third one is omega, which tells the rotation of orbits, and number fourth one is V, which is the true angular position, which tells the position of satellite in orbit. So I hope you understand how we can determine the satellite location in its orbit with respect to the Earth. So moving on to the next topic, we let's see what are the types of satellite orbits. So now let us talk about the different types of satellite orbits. So as we know that the satellite revolves around the Earth in its predetermined and rotative parts known as orbits. So these orbits are characterized on the basis of their elements or some parameters, meaning they are classified in which type of the satellite are revolves in the orbit around the planet. What type of orbit the satellite is revolving around in the satellite, in what kind of orbit is revolving around the planet. So on the basis of that, we have three types of orbits. Number one is on the basis of the orientation of orbital plane. Number two is the on the basis of eccentricity, and number three is on the basis of the distance from the Earth. So now let's talk about one by one what kind of orbits comes under in these three categories. So number one is the first one is on the basis of the orientation orientation of orbital plane. So as we know that there are various types of orientation with respect to the equatorial plane of the Earth. And in the previous topic, we we have I have told you about the angle of angle of inclination, angle of inclination. So so on the basis of that, we have three types of orbits. Number one is equatorial orbit, number two is orbital, and number three is inclined orbit. So if the angle I is at 0 degrees Celsius, then it is and that orbit is known as the equatorial orbit, whose latitude whose latitude is at 0 degree Celsius. And if angle of inclination is at 90 degree, then it is known as the polar orbit. So if the angle I is neither 0 degree nor 90 degree, then it is known as inclined orbit, inclined orbit. So this was the on the basis of the orientation of the orbital plane. So the next one is on the basis of eccentricity, or you can say that on the basis of the shape of the orbit or shape. So in this we have elliptical, circle, parabola, and hyperbola. Meaning, if the intensity E is equal to zero, then that orbit and then the orbit will be circular. And if the if E is between 0 and 1, then the orbit will be elliptical. If it is equal to 1, then the orbit will be parabola. And if it is greater than 1, then the orbit will be hyper hyperbola. Okay, so so um for elliptical orbit, we have one example of the elliptical orbit, which is the Monia Molonia orbit, Molonia orbit, whose with intensity of 0.75. This is the example of the elliptical orbit, which gives 8 hour of which gives 8 hour of service in the Russian orbit. Okay, so a last type of orbit is on the basis of the distance distance from Earth, distance of the Earth. So depending upon the intended missions, depending upon which type of mission the satellite we have to use, the the satellites are placed in the orbit varying different type of distance. So they're classified as LEO, MEO, and GEO. So the satellites which is in the LEO orbit are at a height of 160 to 500 kilometer. So they are very close to the surface of the Earth with shorter with shorter orbital periods, shorter orbital periods, and smaller smaller signal propagation delays. Mean they have a very small signal delays when the satellite had to send some information to the base station. So the applications of these LEO orbits are uh, weather forecasting and many others which are fall into this category. So because the duration is small, the orbital periods are small, so we have to launch multiple satellites into this orbit. So one such example is the iridium iridium constellation, which consists of 77 satellites satellites in its orbit to provide continuous service to the base station. So second is MEO, which is at a height of 10,000 to 20,000 kilometer with um, with 10 to sorry no 10 6 to with 6 to 12 hours of orbital period and the propagation delay is large because they are at a very large a large distance from the surface of the earth, so they are generally employed in communication systems. Okay, so the third one is the geo orbit, which is at a height of approximately 36,000 kilometer, and they their orbital period is equal to the earth's rotational period. So it appears like they are stationary at one point, even though they are moving at a constant speed. Why this is happens? Because they have orbital period which is equal to the earth's rotation period. As the earth rotates, revolves around its axis, these satellites which are placed in the geo orbit, they are also revolves with the same speed, so it appears that they are stationary a, at a point, but that's not the case. So such examples like broadcasting broadcasting signals around the globe is an example of the geo orbit. So this was the types of satellite orbits in which the satellites are placed according to their application. So I hope you understood today's topic. These two topics are somewhat important. So in the next class we will go further. So if you understand today's topic, please subscribe the channel, press the bell icon to get the future notification. How you like it? If you have any, or if you have any suggestion, please tell us in the comment section. And also please like the video. See you in the next video, in the next lecture. Till then, thank you very much.